So we're going to look in this video at how we extend the idea of sine, cosine and tangent to angles larger than 90 degrees. So far, given an angle theta, you can create a right angle triangle, and we know that the sine of theta is given by opposite over hypotenuse, so we call that A, this B, this C. Sine theta would be A over C. Cosine of theta is adjacent over hypotenuse B over C, and the tangent of theta is equal to A over B, opposite over adjacent. And to remember these definitions, we use the word SOHCAHTOA as a memory aid to remember them. But in a right angle triangle, one of the angles is 90, the other two add up to 90. So the room for another 90-degree angle or larger than 90 degree is not there. You cannot have another angle in a right angle triangle being 90 or greater. So this whole business of drawing a right angle triangle and using SOHCAHTOA, this whole thing collapses. So we have to explore what on earth we do to extend this idea. So the first thing that we do is to put, in effect, a right angle triangle on an x and y axis. And I'll do that now. So here we have the origin, here's our angle, and here is x and y axis. Now, as before, if we complete our right angle triangle, the sine of theta would be this distance over this distance. Now, one of the things we do here then is to say, because we're on an origin, let's look at what this distance means. This point here has y coordinate this length, and it has x coordinate this length. Now, in the grand scheme of things, it doesn't matter what size the right angle triangle is with this angle. Suppose this was 30, sine of 30 is 1/2, this would be 1 over 2, this could be 2 over 4. This line would always be a half of this line. This line is a half of this line. This line is a half of this line. It doesn't matter what size the triangle is. So what we do here is we choose this line here, the hypotenuse of the right angle triangle, to have length 1. We then use our SOHCAHTOA. Let's see what happens. The sine of theta is this distance divided by 1. Now, that's the y coordinate of this point. So the y coordinate divided by 1. Any number divided by 1, the number stays the same. So basically, this is now going to be the sine of theta. Let's check it. The sine of theta is the sine of theta divided by 1. That's okay. Sine of theta is equal to sine of theta. That's the y coordinate of this point here. And similarly, cosine of theta, adjacent over hypotenuse, is the x coordinate divided by 1 of this point. So this x coordinate is actually the cosine of theta. So in here, I can put cos theta. Now let's think about that for a minute. This point here has coordinates. Remember, this is a unit length. It's called a unit circle. This is length 1. This point can rotate about the origin, but the coordinates of this point, it doesn't matter where it is, the coordinates of this point will give you the cosine of theta and the sine of theta. The x coordinates, the cosine of theta, the y-coordinate is the sine of theta. So let's see that in a different diagram. Here we are, and as I said, the coordinates of this point P at a unit length from the origin has coordinates cos theta, sine theta, no matter where we move this point. This is the definition of cos theta and sine theta. So for instance, 30 degrees, sine of theta is 1/2. This distance is 1/2. Now, the exciting thing about this definition is that this angle can now reach 90. The cosine of 90, the x-coordinate, is now 0. The sine of 90, that's the y-coordinate, is now exactly equal to 1. And we can move beyond into what's called the second quadrant, and we get angles between 90 and 180, where the cosine is now a negative number. We've gone to the left of the origin. The cosine is a negative number. The sine is still positive. It's above the x-axis here. And so any angle in the second quadrant between 90 and 180 will have cosine negative and sine positive. We can go beyond 180 to get this reflex angle, which is an angle in the third quadrant. Cosine is now negative, the x-coordinate is negative, and the sine is negative. It's gone below the x-axis here. So both cosine and sine are negative for an angle in the third quadrant. That's a reflex angle between 180 and 270 degrees. Extending this, still reflex angle, and this is now an angle in the fourth quadrant. The cosine now has become positive. It's to the right of the y-axis, the right of the origin. It's positive, but the y-coordinate, the sine of theta, is still negative. So cosine positive, sine negative. So there we have a definition for the cosine and sine of an angle theta. It's just the x and y coordinate of a point that rotates around the origin at a distance of 1. Now, several exciting things happen when we do this. If we stop the rotation just now and use this angle, that's 1, and complete the triangle, remember we're saying that the cosine of theta adjacent over hypotenuse, the x-coordinate is cos theta, the y-coordinate is sine theta. Remember, sine theta is opposite over hypotenuse, sine theta over 1. This is just sine theta. Now, Pythagoras' theorem, just a quick look at this. This squared plus this squared gives you 1. We're looking at sine squared plus cos squared equals 1. Sine squared theta plus cos squared theta equals 1. A formula that you should be familiar with, one of the basic formulas in trigonometry. Also the tan of theta, remember from SOHCAHTOA, the tan is TOA, opposite over adjacent. That would mean the tan of theta, sine theta over cos theta. Tan theta is equal to sine theta over cos theta. Again, basic definition in trig. You should know this, you should know this. These need learn. But from this diagram, from the unit circle diagram, knowing that this point, at a distance of 1 from the origin, x-coordinates cos theta, y-coordinates sine theta, cos theta, sine theta, we can get these two formulae from this diagram. Pythagoras, sine squared theta plus cos squared theta gives you 1, and tan theta is opposite over adjacent sine theta over cos theta. That's a marvellous visual way of seeing these two formula. The other thing that we got from this was the fact that as we move around the quadrants, this is quadrant 1, and this is quadrant 2, quadrant 3, and quadrant 4. And in quadrant 1, cos theta and sine theta are both positive. So cos theta, sine theta, both positive, both greater than 0. And since tan theta is this one divided by this one, tan theta also will be greater than 0. Divide two positive quantities and you get a positive quantity. So that's your first quadrant where they're all positive. Cos, sine, and tan, all positive. And if we move into the second quadrant, remember we said any angle between 90 and 180, second quadrant angle, the sine's positive, the cosine's now gone negative. So in this quadrant, we could say the cosine's negative now, and the sine's positive. Tan, therefore, is sine over cos, positive divided by negative, that would be a negative number. So these two negative, only the sine's positive. So let's put that down. Sine is the only positive of these three for an angle in the second quadrant. Moving on to the third quadrant, any angle in the third quadrant, that's between 180 and 270, the cosine, the x-coordinate's negative, the sine also is negative. They're both negative. So we would put cosine being less than 0, the sine of the angle being less than 0, and of course if you divide sine by cos to get tan, negative divided by negative will give you a positive result. So the tangent of a third quadrant angle is going to be positive. So in the third quadrant, the tan is positive. Tangent. Let's move into the fourth quadrant. And in the fourth quadrant, the cosine is positive now. Sine is still negative. It's below the origin now. So cos positive, sine negative. Let's just write that down. Cos is positive, sine is negative, and therefore the tan, which is sine divided by cos, if you divide a negative by a positive, you'll get a negative answer. So in this case, only the cosine is positive. So we'll write cosine positive. So what I've got here is an indication and a diagram that hopefully you're familiar with, that they're all sine cos tan positive in the first quadrant. Sine is the only positive one in the second quadrant. The tan is the only positive one in the third quadrant, and the cosine is the only one that's positive in the fourth quadrant. And remember, the range we've got here is that theta in this case goes from 0 to 90. In this case, theta goes from 90 to 180. In this case, theta goes from 180 to 270. And in this case, theta goes from 270 to 360, not including the 90, 180, 270, or 360. If you get an angle of 90, 180, 270, or 360, it's not in any of these particular quadrants. Okay. Now, something else that we can get from this unit circle diagram, let's concentrate on the sine theta, which is the height at this point is above the x-axis. That's the y-coordinate of this point. And if we have theta being very small, this height gets very close to 0. And certainly when the angle is 0, the height of this point will be 0. The y-coordinate of this point is 0. So we can see that sine theta, if we start at an angle of 0 and move towards 90, sine of theta will start at 0 and increase in value until when the angle is 90, the value of sine is then 1. As the angle then continues to increase, the value of sine is now getting smaller, and it comes back down to 0 when the angle is 180. Continuing in this way, values of sine theta then become negative, and at 270 degrees, sine of 270 degrees is minus 1. The values of sine theta start increasing again until we reach 360 degrees, and the sine of 360 would be 0 again. So let's unwrap that. Interesting, if we decide to plot these values along an axis, let's spread out the results of these values of sine theta along an axis and put the major stopping off points, if you like, along this x-axis. Remember, we said that sine starts off at 0, increases up to 1. That's the y-coordinate is now 1. Remember, this distance, this circle has a radius of 1. It's a unit circle. So sine theta is 1 at 90. So let's plot a value of 1 up there. It started off at 0. And as we continue with the angle increasing to, we said 180, the height of this point, the y-coordinate, is now 0. So the value of sine theta has come back down to 0. And if the angle continues to increase from 180 to 270, the y-coordinate of this point, when the angle theta is 270, the y-coordinate is now minus 1. It's not 1, because remember, it's the y-coordinate. The coordinate of this point has gone negative, the y-coordinate. It's now negative 1. So we've gone down to negative 1 for the value of sine theta. And then as we increase the angle still further from 270 to 360, the value of this y-coordinate increases from minus 1 back up to 0 at 360. So we're back up at 0 at 360. And all the places in between, we unwrap this again, from 0 to 1, you'll discover that the values increase like so. They don't increase as fast as you approach 90 as they were increasing as you left 0. And then they come back down. Completely symmetrical. This, as you can see in this diagram, there's a symmetry about this diagram. What was going on here is exactly the same as what was going on here. So there's this lovely symmetry in the graph that we're building up. And as we continue, remember, beyond 180, the values go from 0 down to minus 1. Just as in, there's a symmetry there too. What was going on in the positive area here is now going on in the negative, for the negative values down here. Tremendous symmetry in this diagram. So, if you like, there's a symmetry in what was going on here and what was going on. See, if you give this graph a half turn about 180, this branch would fit on top of that. And then beyond 270, the values of sine theta increase again from negative 1 back up to 0. And that's reflected in this graph like so. And then, of course, the whole thing repeats itself. So we've got the familiar, but not as good, well drawn as it could be, but there is the familiar sine graph, which we've recovered from this. And of course we could do a similar sort of thing for the cosine values, which are the x-coordinates. They would start off at 1 and go down to 0. So starting off at 1, going down to 0, and then x-coordinates become negative. They go right down to -1 at 180. So we'll get in that case, we would get the familiar cosine graph appearing. And then from 180 to 270, the x-coordinate goes from -1 back to 0, and then from 0 back up to 1. So from -1 back up to 0, and then up to 1 again. And there's the familiar cosine graph. So this graph, the two graphs, sine and cosine, can easily be recovered from this unit circle diagram. So let's look at one last thing that we can use this diagram to help us with, and that's how are the sine, cosine and tan of first quadrant angles related to the sine, cos and tan of angles in the second, third and fourth quadrants. So for instance, if I pick an angle of 30 degrees, for instance, and look at this position. Remember the sine of 30 degrees, that's going to be the y coordinate, that's just a half. And the cosine of 30 degrees, don't matter how it is, but it's root 3 upon 2. These two values will be related to an angle over here. Now that angle will be 180 degrees, that's all the way around to there, minus this 30 degrees. So that's 180 minus 30 degrees. Let me put that in here, 180 minus 30. And this position, if we look at the x and y coordinates, the cosine, that's the x coordinate, will be the negative of this. There was positive root 3 upon 2, it's now gone negative, so that's minus root 3 upon 2. The sine of 150 degrees, which is what this is, would still be 1/2. So the cosine of 150 degrees minus root 3 upon 2, and the sine of 150 degrees 1/2. So the sine 30 and 150 are exactly the same, but the cosine of 30 and 150 are opposite signs. You can see the next position would be down here, and that would be taking an angle of 180 plus 30 degrees. Let me write that in, 180 plus 30 degrees, that's 210 degrees, and in this case the cosine of 210 degrees would be minus root 3 upon 2 again, and this time the sine of 210 would be minus 1/2. This is the positive 1/2, we've now gone below the x-axis, same distance, that's minus 1/2. So 180 plus 30, cosine of 210 and the cosine of 30, opposite signs. The sine of 30 and the sine of 210, opposite signs. So one last position, that's the one here, which, as you can see, is we go right round to 360 and back 30, so it's really 360 minus 30. That's 360 minus 30, 330 degrees. So that large angle there, and in that case the cosine of 330 degrees is back to positive, that's the x-coordinate, back to positive root 3 upon 2, and the sine of 330, well, that'll be negative 1/2. same as this one. So the cosine of 30 and the cosine of 330 are exactly the same. The sine of 30 and the sine of 330 are opposite sides. So you can see that the first quadrant angle of 30 degrees has the same numerical value as sines and cosines of 180 minus 30, 180 plus 30, and 360 30. The root 3 upon 2 and the half appear in all quadrants. The only difference is the signs. The signs are different. But crucially, 180 minus, 180 plus, 360 minus. If you like, these are doors that open the angles of the second and third and fourth quadrants using the first quadrant angle. If this was theta degrees, this would be 180 minus theta. So we go all the way around to 180 and then minus it to get an angle in here that has the same numerical values. It might differ in the sign. And here would be 180 plus theta. So we go all the way around to 180 and add on the first quadrant angle to get the same numerical values. In this case, they're both the negative of what the first quadrant sine and cosine are. And then the fourth quadrant, 360 minus theta is if you like, the way of getting into the fourth quadrant angle using the first quadrant angle. So 180 minus, 180 plus, and 360 minus. Same numerical values, they only differ positive and negative.